Welcome back. This is episode 2 of Binomial Coefficients. Let's jump right in. So first I want to pose a question to you. What is n choose 0? Well, going back to our definition, n choose 0 is the number of 0-element subsets of an n-element set. Okay, so you can imagine we have some set with n elements, yada yada, 1 up to n, for example. How many 0-element subsets can we derive from this? Well, just 1, right? Just the empty set. So the answer to what n choose 0 is just 1. By the way, as a little bonus here, what about n choose n? Well, it's kind of a similar argument, right? If you have a set with n elements, how many subsets of that have n elements? Well, just the entire set, right? That's the only subset you can make that has n elements. So n choose n is also 1. Okay. What is n choose k when k is larger than n? This, I think, is also just best to see by just expanding out the definition. n choose k is the number of k element subsets of an n element set. But k is larger than n, so something's a bit fishy here, right? Let's think about some set here with n elements. How can we make a subset from this that has k elements? So you can imagine, I don't know, we have some set here, yada yada, right? There's k elements in here, and k is larger than n, so the subset has more elements than the original set. Now, that's just impossible. Can't be done, right? You can imagine we have, this set 1, 2, 3. How can you make a subset of 1, 2, 3 that has 4 elements? You can't, right? So in this case, n choose k, when k is larger than n, is just 0. Okay, great. I want to change gears a little bit, and now talk about an example that'll come in handy. Say you are forming a student council consisting of 3 students, and there are 5 nominees to choose from. So this is exactly the setup we had in episode 1. But this time, one of the nominees is named Bob. How many different councils can you make? Well, okay, I think your first guess looking at this question should be, what on earth are you asking? What does Bob have to do with anything, right? We still have 5 nominees, we still have to choose 3 students. This should still be 5 choose 3, which is 10, right? This is pretty obvious. And you're totally right. I'm not trying to fool you here, but I want to show a different perspective on this question. So the number of councils that we can make, I'll just write this as number of councils. Well, this equals the number of councils with Bob plus the number of councils without Bob. Okay, I haven't really done anything here. But notice now that this is kind of a different question. Okay, we can ask how many councils have Bob in them, right? Well, we have our 5 nominees, right? We have, I think I wrote them as A, B, C, D, and E. Let's say Bob here is B. That's the sensible option, right? So how many councils do we have with Bob? Well, okay, with Bob, well, what do we need to choose? We need to choose 2 more students, right? So choose 2 more students. And, well, now we have 4 nominees, right? We have A, C, D, and E to choose from. So choose 2 more students from 4 nominees. So the number of councils with Bob, right? What is this question really asking? Choose 2 more students from 4 nominees. We know how to answer this. This is exactly 4 choose 2, which is 6. What about without Bob? Poor Bob did not get elected. Well, here we still have to choose all 3 students, right? So we have to choose 3 students, as before. We still need 3 on the council. But we're still picking from 4 nominees, because we can't choose Bob, right? Because Bob's not here. So the number of councils without Bob is, well, 4 choose 3, which, well, you can work out the details, but it's 4, right? The reason why it's 4 is because each of these corresponds, each of the 3 element subsets here, so if you imagine have 1, 2, 3, and 4, and I look at all the 3 element subsets, so 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4. So, well, okay, here I've worked it out, but the intuition you should have for this is that when you have something like 4 choose 3, each of these excludes 1 element. So this one doesn't have 4, so this has no 4. This one doesn't have a 3. This one doesn't have a 2. This one doesn't have a 1. So whenever you have something like 4 choose 3, in a way you're really listing out all the ways you can exclude each element. So this is just going to be the number of elements in total, right? So what I'm trying to say here really is that if you have some kind of n, choose n minus 1, this is always going to be n, because you're always going to exclude 1 element in each subset. Okay, that's a lot of talking. Let's get back to the point. The number of councils with Bob plus the number of councils without Bob. So the number of councils is, well, the number of councils with Bob is 6. The number of ones without him is 4, so it's 10, as we expected, right? We did not break anything by analyzing it this way. So this might seem like a lot of work for not much gain, but this actually provides a bit of an insight that we're going to use right now. That's in what's called Pascal's rule. This is a very, very powerful result about binomial coefficients. So it says n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. And I'm restricting it to n and k greater than or equal to 1 because we haven't made sense of negative binomial coefficients yet. There is actually a world where you can make sense of that, but not for now. Okay, this is our first big theorem. How might we prove this? Well, we can think of Bob, right? We can think of Bob. So what we established was that when you're trying to form a council, you can count the councils separately, those with Bob and those without. And similarly, we're going to do the same thing here. Okay, so let's say we have some n element set, right? By the way, when I say proof in this series, I'm not going to be extremely mathematically rigorous. I'm more just trying to convince you or provide an intuitive argument rather than a fully detailed proof. So, okay, we know that n choose k is a number of k element subsets here, right? So maybe I'll write that out. So n choose k is the number of k element subsets of this n element set, or any n element set. Okay, but what about Bob, right? Let's think of Bob loosely here. Bob will be 1. 1 in this set, okay? So this is the number of k element subsets with 1 plus the number of k element subsets without 1. Okay. What is the number of k element subsets with 1? Well, remember, if we have 1 included, we have to choose. Remember, we're choosing k things in total, so we have to choose k minus 1 more things, more numbers really, from n minus 1 things, right? Since we already have 1 included. So this first term here is just n minus 1, choose k minus 1. Okay. Let's look at the second one here. The number of k element subsets without 1. Well, here, we still have to choose all k things, right? We haven't chosen anything yet. So we have to choose k things. But again, it's from n minus 1 things. Because we can't include 1, right? Poor Bob, poor number 1, is left out. So what is this? The number of ways to choose k things from n minus 1 things? This is just n minus 1 choose k. Okay, and this is exactly the result we want. We want n choose k equals m minus 1 choose k minus 1 plus m minus 1 choose k. And we're done. The best part about math is always putting the square at the end of the proof to show that you're done. Okay, again, not a fully mathematically rigorous argument, but hopefully this convinces you. Okay, this might look like a cool fun fact at first, but this is actually much more powerful of a result than it initially lets on. Let's see why. So let's fill out this table for binomial coefficients. This is the real meat and potatoes here of why this result is powerful. It lets us do this. And it actually provides a recursive definition for binomial coefficients. So let's start. We have 0 choose 0. So here n is the row and the column corresponds to k. So this guy here will be 0 choose 0, for instance. Right? This one here will be 0 choose 1. This will be 0 choose 2. You know, this guy over here will be 2 choose 3, so on. Right? I'm going to erase this here because we're going to actually fill in the actual values here. Right? Okay. What is 0 choose 0? Well, we established earlier that n choose 0 is 1 for any n. And just logically, what is the number of 0 element subsets of 0? It's just 1. It's just the empty set. So it's just 1 here. Okay. What about 0 choose anything else in this row? Well, for anything else in this row, we have that k is bigger than n, right? 0 choose 1, 0 choose 2, 0 choose 3. These are all just 0. So 0, 0, 0, 0, 0. Okay. And I also want to fill out this first column as well. Right? We can use the fact that n choose 0 equals 1 to just immediately list these all out as 1. Perfect. And now, we actually don't have to really do any more work. The rest of it is actually already done for us by Pascal's rule. What is 1 choose 1? Well, we know it's 1, but another way we could figure out that it's 1 is just by summing up these two entries above it, right? So, for you to remember, Pascal's rule is that n choose k is n minus 1 choose k minus 1 plus n minus 1 choose k. Essentially meaning, to find any entry in this table, we look on the row above it, and we look top left and top, and we sum those two. Okay, so 1. And now we can literally just repeat this. So 0 plus 0, 0. 0 plus 0, 0. Okay, I'm not going to draw out the arrows for all these zeros, but you get the idea. 1 plus 1, we finally have something larger than 1. 2, okay. 1 plus 0, 1, 0 plus 0, 0, 0 plus 0, 0, 0 plus 0, 0. Okay. Now we have some bigger numbers. 1 plus 2, 3. 2 plus 1, 3. 1 plus 0, 1. And then it's all zeros. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 0 is 1 and 0. 1 plus 4, 5. 4 plus 6, 10. 6 plus 4, 10. 4 plus 1, 5. 1 plus 0, 1. Okay, not too bad. Of course, the binomial coefficients don't stop here. You can have as big of an n or as big of a k as you'd like. You can imagine this table will go on forever, but you can imagine this gives you a very quick way to compute very large binomial coefficients. There is a better way as well, which we'll see later. And yeah, this is a great way to just kind of look up any values you want. But there's actually something a little more going on here. Do you ever wonder why I called it Pascal's rule? Well, I didn't invent the name, but why is it called Pascal's rule? Well, maybe if you squint your eyes hard enough and you can imagine rotating this triangle that I've made here, you could notice, right? Maybe I'll draw it in blue here. So if we look at all the filled in values that we have here, and you imagine kind of rotating this to look more like a centered isosceles triangle. What is this, really? This is literally just Pascal's triangle, right? Each thing is the sum of the two things above it. So, this 10 here you get from just summing this 6 and this 4. So the binomial coefficients are literally the entries of Pascal's triangle, right? So what is this 1 here? This 1 here is 0, choose 0. This one is 1, choose 0. This one is 1, choose 1. Here we have 2, choose 0, 2, choose 1, 2, choose 2, so on, right? Each row corresponds to your n, and each entry corresponds to your k, essentially. So this is a very cool fact, I think. It's a great way to kind of like visualize binomial coefficients and also to provide a little insight into Pascal's triangle. You may have wondered, is there anything special about the numbers in Pascal's triangle? Do they have any special kind of meaning? And yes, they absolutely do. These literally are the binomial coefficients. So this is like a really amazing fact, in my opinion. I hope you enjoyed this episode, and I hope to see you around for part 3.